this opportunity. So as mentioned, I will talk about this is a very general talk, but with this central problem, why electron and neutrino are time crystals. So what I will show in a moment that it's very closely related to quantum phenomena in both directions. And what does time crystal means? So the Wikipedia article is that something what in the lowest energy state is already oscillating. Yeah, so for example, pendulum is oscillating, but it's not time crystal because in the lowest energy state it will slow down to zero. Yeah, so the question is, could we do something what oscillates in the lowest energy states? And after a year, so it was introduced by Frank Wilczek, 2012, but then there was a mistake, and later then they proved no-go theorems, that it's impossible. Yeah, so now they say it's not possible. Now they focus on period doubling I mentioned in a moment. But the question is, are there time crystals? And there are, and in relativistic quantum mechanics, we need them because there is the phase evolution, like exponential of minus E energy times T divided by hbar, Planck constant. With energy in relativistic, we need to use mc square. The mass of the particles literally propels the clock of the particle. Yeah, so the resting particle, this m is already there in the resting particle. There is already oscillations in the resting particle, and we know it. So literally, energy minimization leads to oscillation. Yeah, so we need to understand why minimization of energy already has this non-zero time derivatives, some periodic process. Yes, because the mass is some integration of some Hamiltonian of the field of the particle. So we know well these two examples. So one is neutrino oscillations that we start with produce one type of a neutrino, and after some time we measure its flavor, and it turns out it's some different neutrino. Yeah, so we have this equation, but with three different masses for the three flavors. And the second example is the electron clock. It's called the Broglie clock, originally proposed by him, by Louis de Broglie, also the Zitterbewegung. And also it can be viewed as through just angular momentum. Yes, resting electron has angular momentum. It means something rotates. It's not the point, it's the field. Particles are the construct of the field. So the field is rotating, yes, like here. Not the point, but just the field. And the clock itself, so having some rotation, it also has periodic process, so it can also act as a clock. We can also view it this way. And the clock itself was also directly experimentally confirmed for electron in this experiment, 2008 experiment. So they prepared high energy electrons, 81 MeV. Thanks of that the distance between ticks of this clock of electron agree with the lattice of silicon. And now shooting these 80 MeV electrons to this lattice of silicon crystal, if they agree, then they get increased absorption. Yeah, so these are the two absorption that shooting through the crystal, the number which pass is much lower. Yes, so literally there is a resonance between the clock of the electron and the lattice of the crystal. Yeah, so the resting electron and neutrino are confirmed experimentally that they are already oscillating like the time crystal. And so the question is how to do it against these no-go theorems. They say that it's not possible, but nature shows it's possible. So yes, so we need to do it. We need to show why energy minimization already leads to oscillations. To understand quantum mechanics, it is crucial for quantum mechanics. Yes, from one direction, it is required by relativistic quantum mechanics. From the other, I will show that having the time crystal, there are also coupled waves. It creates coupled waves, and the coupled waves, the pilot waves, lead to quantum-like phenomena. So this is very close to quantum mechanics, to understanding the foundation of quantum mechanics, why there are time crystals. Yes. So my solution I will talk about is like here, that we need to make that energy minimization leads to the oscillations. Yes. So we need to have in Hamiltonian this kind of term. So this is the term I will use. This is curvature square term, like here, and it has the spatial derivative. So the shape of the field of the particle, so the presence of the field of the particle will give tendency for non-zero time derivative. Yes, because there is square and there is minus. So it is curvature square, it is Lorentz invariant term, and it will automatically appear from the models I will show. So this kind of term will literally give preference that in presence of particle, where this spatial derivative of the field is non-zero, there appears tendency and negative tendency for non-zero time derivative. So for the some oscillation, some internal process of field of the particle. So exactly as we need. Yes. So this will be some late, but there will be a lot of qualitative discussion here, and this is just the final some discussion. So but if it's somebody doesn't like this kind of mathematics, there will be a lot of pictures. Okay, so let's start with some simpler looking experiments. So now the time crystal people mostly focus on so-called they call discrete time crystals. That there is some periodic process, and they have, for example, period doubling, some integer multiplicity of this original period. So it can this period doubling can be also obtained classically. So I will briefly show this very nice series of experiments. So you probably know these are these walking droplets that started by Yves Couder experiments, that there is this shaker literally. So this something what made everything oscillate. Yes, so and there is this fluid tank, and then there is a droplet, and this droplet, depending on parameters, have various behavior. So here is the phase diagram. So based on the diameter of the droplet and acceleration. So here is some simple bounces, some more complicated, and here it creates a sonic wave. So here are some plots for the a few phases here. So here is the simple bouncing. So here you can see that here is time, and here is the position. So here is the surface, and here is the droplet. Yeah. So here you can see that it is the droplet has the same period as the shaker. Yeah. But here you can see a period doubling. That the shaker has the droplet has two. So here is period doubling. Yeah. So the shaker has two steps for. Two steps per one bounce of the droplet. Yeah, so exactly as they need. So the period doubling the time crystal people search for is very nicely shown here. But this experiment has many other similarities with physics, with quantum mechanics. So if they look at these droplets that they have, so now these droplets get these couplet waves. Yeah, so we have a droplet, and then it is bouncing. It's in this W, this walking regime they work in, we'll have a couplet wave. So we have classical wave-particle duality object. Yeah, so we have the corpuscle as the droplet, but it also has this couplet wave, and it acts as the pilot wave. So having this shaker, having this periodic process. So here by external shaker, but finally we would like to have it as internally for electron itself. But having it couples some waves around, and now they made many very nice beautiful experiments recreating many quantum-like phenomena with these bouncing droplets. For example, this interference on the one slit or double slit, that looking at paths of such droplet, this pilot wave, this droplet creates acts as a pilot wave. It controls the path of the corpuscle. So finally the statistics of these corpuscles becomes interference-like. So taking quantum mechanics. Or they get tunneling, that this shaking acts as a fundamental noise. It has a very complicated shape. So once it allows to pass a barrier, the other times it doesn't. They get very nicely this orbit quantization. So we have the droplet is making some orbit, but it cannot make any orbit. It has only quantized radii here, for example. So why? Because this couplet wave has to become standing wave. Yes, exactly as in Schrödinger equation. It describes standing wave. Yes, because intuitively the standing wave, if it's not standing, then it should radiate some energy. So until it gets to standing wave, and exactly like this, they get with these walking droplets coupled with wave, yes. And also they get a double quantization, both the radius, but also the angular momentum. And there are some examples, these orbits that they get classical orbits. And recently they also get CHSH variation with this kind of setting that they have these two pairs and they count the number of appearances and then the inequality is above the classical limit. So classically looking, but classical field theory is much more sophisticated than required. So I'm not reading the comments. So if something is related, please unmute and interrupt me because I don't have time to read the comments now. Okay, so generally there are lots of hydrodynamical analogs. Yeah, so we have electrodynamics and hydrodynamics. The main difference between them is the speed of propagation. So here is the speed of light, here is speed of sound. But if having zero viscosity, having superfluid, so here is with viscosity, so having zero, the equations become very similar. So hydrodynamics and electrodynamics are very similar. The most important, I think, the correspondence here is that the magnetic field and this A field for vector vector is corresponding to this omega vorticity and the speed of fluid. Yes, and for example, using this analogy with this orbit quantization, they get literally Zeeman effect as Coriolis force. Yes, the Lorentz force becomes the Coriolis force. So having these quantized orbits and now rotating this fluid tank, they can increase or decrease the radius. So exactly like in Zeeman effect, but using the Coriolis force in place of Lorentz force. Yeah. So this analogy is very close and nice. Yeah, so and also finally there is this Casimir effect. Yeah, so it's thought generally as a very quantum-like effect. However, you can have a video when they get this Coriolis force. Again, they need the shaker, and now making the shaking, the wave between the plates is restricted, while the outside is not restricted. So finally they are literally attract. And these articles say that it might also happen for with the ships. So again, but the question is, what is the shaker? Yeah, so we go back to this question: what propels the clock? Why everything rotates? Yeah, so here they use external shaker, but with electrons you would like to have them as time crystals. That the propulsion of that the shaker themselves are not some external shaker, but they are inside the electrons. All the particles have this clock, and it makes all this shaking. Yeah. So that's the general question we can discuss. So what is this fundamental noise? So I think it's governed by just these clocks of particles, of electrons and other particles, but many electrons. Okay, so let's go to particles. So there is a big question: what is a particle? Yeah. So in standard view, which is perturbative approximation, particles are imagined as perfect points. However, we have to remember that perturbative is approximation. Yeah. So it's very similar to apple plus apple equals 2 apples. Yes, it's true, but it's not fundamental. Below there is, we can ask about deeper structure of this apple. Yeah. So finally, having this Feynman diagram, electrons are points there, but we should be able to ask about field configuration this Feynman diagram represents. Yeah. So the question is, if you have electron here, what exactly is the field configuration here? Yes. So for electron, as this is electric charge, it has to be 1 over R square electric field at least. And so there is very complicated field configuration behind these particles, and you would need to find to try to understand it. So it's called non-perturbative picture. But we ask finally about these field structures. So for electron, we know this electric field, what is asymptotic behavior, but we need to regularize it in the center of electron, what's the difficult parts, and I mention later. But also for neutrino, yeah. So neutrino is, nobody asked about field configuration of neutrino. However, there is this recent experiment, quite recent experiment, which says that neutrino is like larger than 6.2 picometers, so 1,000 times larger than nucleus. So it works like this: that this beryllium decays into lithium and produces neutrino, and based on this energy spectrum with Heisenberg, they can get this delta H larger than 6,2 picometers. So, but the big question: what's happening there? What is the field configuration inside this huge size? So we shouldn't think about neutrino as perfect point. So this is, we can as in the approximation, but fundamentally there are very complicated field configurations of relatively huge size. You know, so 1,000 times larger than nucleus. What is the field configuration hidden in this abstract name in this huge region? Okay, so for electron again, so we can represent it as perfect point. However, it's much more complicated. Yeah, so we had being point charge means electric field configuration. So it's relatively complex, and there is a problem in the center. What's happening in the center? So mainstream doesn't even ask. Then there is magnetic dipole. Yeah, so it is tiny magnet, what is used in many processes like Larmor precession, spinel. Then is gyroscope. It's an angular momentum, but this is not a point rotation of the point, but these are field objects. This is rotation of the field. Yeah. So the question is, how does it look, this rotation of the field? And there is this electric charge is quantized. Yeah. So we cannot have pair creation of half electron plus half positron. We have to have complete the elementary charge. There is some restriction of Gauss law. Where is this restriction of Gauss law I will talk about? Yes, also this is very important. If you don't have charge quantization, then you can get half electron. Why we don't see half electrons? Okay, so and there is this clock. Yeah, so again, this is confirmed experimentally in various ways, and we can see that this is a consequence of this angular momentum, that something rotates there. Yeah, so we can call it clock. Yeah, so I think this is very related. So the question is, what is the field configuration? And here is this view. I think it's close, so maybe I can show some animation. So here is the electron. Here is the field configuration which satisfies the properties, the required properties of electron. Yeah, so it has quantized electric charge as topological. Yes, it's not allowed. Half of this is a Hedgehog topological charge I mentioned further. So we cannot have half of topological charge. Yeah, so it's quantized. We cannot have fractional here. Okay, quarks. I will talk about quarks also, sure. And there is angular momentum. The field itself rotates, not the point object, but the field itself. Yeah. So this field configuration has quantized electric charge as topological, angular momentum, which can also be interpreted as the clock. And it also is the magnetic dipole moment. This rotation plus electric charge. Okay, so I will try to convince that this is the proper picture evolution of the field of the electron in non-perturbative picture. Yeah, so we would like to go from these abstract Appel's Feynman diagrams into field configurations, into non-perturbative picture. So if there is something important on the chat, please tell me. Okay, so some general view. What is the difference between classical and quantum picture? Yeah, so there is. They try to say that there is some huge barrier between them, but maybe it's not barrier. Maybe it's just perspective. That there is the same setting, but we just view them from different perspectives. Yeah. So, for example, couplet oscillators. We can define them. We can describe them classically, but then we can go to these normal modes, and we get unitary evolution, like quantum mechanics. Yeah, so it looks like quantum mechanics, the same system, but different perspectives. Yeah. Then we can have crystals. We have this kind of ordinary differential equation, but we can go to normal modes, and they become the phonons, which in perturbative quantum field theory are described as particles. Yeah. So, but these are just different perspectives on the same system, just going to Fourier basis. So, but the difficult part is the infinitesimal limit. Yes. So, as mentioned, like this orbit quantization, it is obtained for the both in droplet. They also get this orbit quantization because the couplet wave has to become standing wave, getting the Schrödinger equation. There are many more examples. And finally, how to get multiple particles. And again, there are observed in for example, in liquid crystals. I mentioned that in liquid crystals you can have topological charges and an effective Coulomb interaction between them. So quantized charges Coulomb interaction. So we can try to translate what does given Feynman diagram means in terms of fields, non-perturbative picture. Okay, so where the quantum magic comes from? Yes, I would say that the main magic is the Bell validation, which comes from Born rule. So where the Born rule comes from? So here is a simpler view that imagine you have this infinite potential well, 0, 1 range. Yeah. So the question is, what is the stationary probability distribution? Yes, we have just 0, 1 range. We have some Walker. And what stationary probability distribution should we assume for this Walker? For standard classical view, uniform ensemble of positions, Boltzmann ensemble of positions, this is uniform distribution. Yeah, so this is trivial. However, in quantum mechanics, we say sine square. Yeah, so this is completely different. So where this sine square comes from? So assuming a complete path, ensemble of complete path. So now instead of thinking about points, we think about paths as our fundamental object. So this is crucial that all the quantum mechanical descriptions you work on 4-dimensional scenarios. Here paths, finally the Feynman diagrams. These are 4-dimensional scenarios. We cannot think about points. This is approximation, this classical approximation. Wanting to make real quantum mechanics, we have to go to 4-dimensional scenarios. And using ensemble of paths, this paths, so let's start with paths in one direction that we are now, and now we think about all the paths toward future and assume uniform distribution among them. This would lead to first power of the amplitude. Or also using the pass ensemble. Yeah, so using this one directional ensembles, we can mathematically show it leads to first power of the amplitude. But if you use ensemble of full paths, now we have to meet these two half paths. Yeah, so we have to draw some to get some position. We need to draw it twice from here and from here. We need to multiply these amplitudes, and we get the Born rule. Yeah, so the Born rule comes from time symmetry that we don't have to work on half paths, but we work on full four-dimensional scenarios, which now are cut in this given moment of time, this hyperplane. Yes. And this is also very popular in scatter matrix. Again, one amplitude comes from the one direction, second amplitude from the second direction. Also, it's called two-state vector formalis. That we need to multiply two amplitudes because we have past and future, and we can switch them. There's the CPT symmetry. They are very similar. Yes. Also, I think this is where the magical quantum mechanical situations like the Born rule Bell validation comes from. The time symmetry. It is. We need to multiply two amplitudes because one comes from one direction, second comes from the second direction. So it assumes uniform path ensemble, but for example, in Ising model, we also have uniform ensemble of paths, or generally Boltzmann ensemble. And this way we can also get the violation of these Bell inequalities. So here is the simplest inequality of this type. So if somebody says that he has violation of Bell inequality, I ask about this inequality, which is much simpler. So it's very difficult to violate it. So just tossing 3 coins, at least 2 of them give the same. It's absolutely obvious, but somehow quantum mechanics can violate it. Yes. So to prove it, we have three coins, ABC, binary variables, and now there are 8 possibilities. So this probability are these 4 ones, these 4 cases, plus those, and we see that everything is at least 1. So whatever joint probability distribution we choose, this has to be at least 1. Yeah, so we have just proven this inequality. Yes, by just this trivial application of Kolmogorov third axiom, that probability of alternative of disjoint events is just sum of their probabilities. However, in quantum mechanics, we replace this Kolmogorov axiom with this Born rule. Yeah, so we just first sum the amplitudes, then make square. So this is the same question but different answers. Yeah, so it's not a surprise that having inequalities derived with one rule, the Kolmogorov axiom, changing this rule, this inequality does not have to hold all the time. Yeah, so we can easily get using this amplitude, we can violate this inequality. And for already in Ising model, because this is also path ensemble now of spins. Yeah, so having this sequence of three spins, with interaction forbidding these two cases, these two zeros. So we forbid 3-spin up, 3-spin down. Doing so, we get the probability to get variation to 0.6 of this inequality. Yes, so we can also get it for Ising model because Ising is path ensemble, Boltzmann path ensemble in space, while quantum mechanics is Feynman path ensemble in time. So they are mathematically very similar. And for example, Born rule comes from symmetry. Both of them have this symmetry. Okay, so what about measurement? So maybe let me tell briefly how do I see measurement? And I think the simplest case of the measurement is the Stern-Gerlach experiment. You have just magnetic field and magnetic dipole. So having magnetic dipole in magnetic field, it starts to precess. Yes, because of this torque becomes non-zero. So this torque is zero when they are aligned or anti-aligned. So yeah, so if it's non-zero, then we have the precession, what means additional energy, and it means varying an electromagnetic field, and varying electromagnetic field radiates energy. Yeah, so thinking about just classical thinking says that it should radiate the energy and go to aligned or anti-aligned state, exactly as observed in measurement. Yeah, so what is missing in quantum mechanics is that works on this point electron usually, while we have also electromagnetic field. To include this radiation, we have to include electromagnetic field into our considerations. And yes, so it is done that we have ground state atom plus the surrounding this electromagnetic field, and we go to this excited from excited to ground state, and then the photon goes to this field. So we can do it with this very abstract quantum mechanics view, but finally we need to include this electromagnetic field to get this measurement. So this way we can imagine measurement as preparation of situation that there are, let's say, two minima, and our system goes to one of these two minima, yeah, by somehow radiating energy. Okay, so now let's go to these particles in liquid crystals. As I mentioned that we can get electromagnetism very close to electromagnetism with just hydrodynamics. However, it itself does not have the particles. They add it with the droplets, but now we like to have the particles as something inside this fluid, this medium. And it can be obtained, it is obtained experimentally for liquid crystals. Yeah, so now beside the just hydrodynamics, there are also these configurations, like here, that there are topological charges. Yeah, so you have charge, anti-charge, topological. So you have charge quantization as topological. But here they look at the distance versus time. And we can see that there is a long-range interaction. They can fit some polynomial type of interaction. So just working on this. So this way, that's very extension of this hydrodynamics to topological charges. We can get quantized topological charges and Coulomb interaction as effective interaction. Yeah, so we have just a field, and it allows for this particle like situations, and effectively they behave like Coulomb interacting. So we can get toward particle physics with just a field. Yeah. So the question is, how far can we take this analogy, and I should try to show that very far. Yes. So here is some more formal. So there is this problem that standard electromagnetic does not have charge quantization. That the Gauss law can return any real number, while in nature it can only return integer multiplicities of elementary charge plus quarks, as I mentioned in the moment. So how to build this charge quantization inside the Gauss law? And it can be done. There is this topological Gauss-Bonnet theorem, which looks very similar, but returns integer multiplicity of something. Yes. So how to get it? So here is curvature. So we just need to take some deeper field, like here, this n field, field of unitary vectors, take its connection, curvature, and define this curvature as our electromagnetic field. Yes, this way our Gauss law will count the topological charge. So it's a very simple way to get built-in charge quantization. However, doing it standard way, we get the magnetic monopoles. So we don't want magnetic monopoles. Nobody has seen them, so probably they don't exist. So we can use the dual formulation, this star here. It means just switching electric and magnetic field. So now these monopoles becomes electric monopoles. They become charges. Yeah, so charge particles. So this is exactly what we need. We have just electric charges and magnetic dipoles later. So exactly as needed. So we have to use these Dirac-like monopoles, but in dual formulation to make them electric instead. So there is this freedom between choosing this dual or standard formulation, and the standard one I think is incorrect. We should switch them, and we can do it. So now we can see that this taking apart these two topological charges, the energy increases as the tension of the field, yes, visually. And now let's try to formalize it. So now we have these two topological charges. Here are the same plus topological charges in various distances. Here are the opposite, plus minus, yes, and the colors are the energy density for some chosen Hamiltonian, I was saying the moment. So here is the Hamiltonian. Hamiltonian is, as previously, this is this is curvature square. So this like electromagnetic, this F squared, sum of this F field squared, but this F is curvature of some deeper field. So this is the curvature. So this is this F field as curvature of some deeper field. And now we have this Hamiltonian, and we integrate this Hamiltonian, getting energy of given configuration. And here is numerical calculation, the dots. And the line is the fitted 1 over R potential, and we can see that this is exactly Coulomb potential. Yeah, so integration of Hamiltonian, calculating energy of this configuration, you get exactly the Coulomb potential. Yeah, so we can get, so we just work on the field, and it automatically gets quantized charges, which get the Coulomb interaction because of effective Coulomb potential. If our Lagrangian is Lorentz invariant, then we get also the magnetism, because yes, we having Coulomb plus Lorentz invariance, we get entire electromagnetism. Yeah, so we can relatively easily get entire electromagnetism for these quantized charges. Simple model of electron. Okay, so there is some problem. So in the center, there will be singularity. The energy will be infinite, so we need to regularize it, and there are used this Higgs-like potential. So here is Higgs potential. So it prefers unitary vectors. However, it allows them to deform the center. Yes, because otherwise the energy will be infinite. It is required not to exceed mass of electron with energy of its electric field alone. Yeah, so here is energy of electric field starting from this 1,4 femtometers. If you do it, we already get the mass of the electron from this electric field alone. So there is a problem. So we need to deform this field in this like 2 femtometer radius. So it cannot be perfect point. We need to deform it, and these Higgs-like potential are used to deform it. Yes, so usually you have to magnetize. However, in the center of singularity, the field has to deform. So electromagnetism has to deform not to exceed mass of electron with energy of its field alone. Yeah, so here is this energy of this field alone, this red curve, and normally you'd get to infinity, but now we activate this potential and we allowing to get to zero. So finally, then the final energy is zero instead of infinity. So the question is, does this regularization of singularity to finite energy have some experimental consequences? And turns out yes. So this Coulomb potential turns out slightly deformed. Yes, so for very close distance, like femtometers, the dots are this calculated numerically, this Coulomb potential for these regularized singularities. You can see that the Coulomb force is slightly stronger in very short distance. And this effect is known as the running coupling. Yeah? So the alpha is increasing in very high energies. And this it turns out to be in agreement with this numerical effect. So this way we can see the running coupling, this modification of Coulomb interaction in very high energy, that what means very short distance, as just required by this regularization of singularities. Okay, so here I have some argument. Maybe let me skip it. And now let's go further. So beside these point light defects, as I mentioned, which are natural candidates for electric charges, so we also have these topological vortices. So the question is, do we have these topological vortices in particle physics? And it turns out, yes, there are so-called flux tube quark strings, that the quark and quark are connected with this one-dimensional structure, which has asymptotically very large energy. So I mentioned further. So we also need these topological vortices in this microscopic picture for these quark strings connecting quark anti-quark. And here is so finally to get both, we need to combine them. We have both the topological vortex, but also charges, these fractional charges. Yeah, so for quark, so performing this inward field rotation by pi, we will get a hedgehog. So we will get elementary charge. But doing it by pi third, we get fractional charge as for quark. Yeah. So now we have the quark. However, there is a conflict between them this way. Yeah. So there is something wrong here, and it leads to linear energy. Okay, in a moment. So okay, so having these quark strings, there is very important string hadronization. So in LHC collisions, that they assume there is created these quark strings and it decays into all the particles. So knowing they are topological vortices, there are many articles in this way, we just need to find the correspondence, what topological vortex can decay into, and what they observe in LHC collisions. And going to be this correspondence, everything seems to agree, as I mentioned further. Okay, so we have this cross-section of this vortex, and again, it has charge, and it has topological charge. So topological charge, like here, going around a vortex, we count how many times the field rotates. Yeah, so here it rotates once, so it's +1 charge. But we have this Gaussian invariance that we can rotate everything by pi, so we say still +1 charge. Here you have -1. Yeah, so going around, we need to go rotate -1. It is +2. But you can also have 1/2, because if having that this field and this field is the same, then just rotating the field by half of the rotation, full rotation, we get the same field. Yeah. So with this definition, going around, we perform 1/2 rotation. So this is exactly like spin 1/2. So they use it for liquid crystals, and to see that it's as spin. There is this quantum rotation operator that spin S particle rotated by theta angle makes that quantum phase rotates by theta times spin. Yeah, so this is exactly what we have here. Yeah, so here rotating by theta, the phase will rotate by theta times 1/2. So it is in perfect agreement with the spin situation. So the spin is this cross section of these topological vortices. I think this is the most appropriate interpretation. And we have this clock, so we have this kind of evolution. Okay, so now we have these vortices. So let's think about it. So we cannot avoid them. So they appear in superfluid, superconductor. So literally they are these quantized vortices. And as mentioned in particle physics, they correspond to these quark strings, that this quark anti-quark, and between them there is this increased energy. Yes, and in this view, indeed, we have this topological vortex, we have this fractional topological charge, anti-charge, yes, quark anti-quark, and between them there is some conflict. And this conflict, intuitively, which will have asymptotically linear energy. Yes, so, and indeed, in QCD there is this corner potential, so-called, but there is Coulomb at the beginning. There are charges, so there should be Coulomb at the beginning, indeed. And then there is linear behavior, yes, indeed, because the cross section will be approximately constant. So asymptotically this linear. So we have just derived the corner potential. So basically, we have charge quantization as topological. However, we can bend it, like here. We can have fractional. It's still for fractional, but at high cost of energy. At cost approximately proportional to distance between these fractional charges. So the total energy has to be the total charge has to be quantized, but locally it has to be bent at a large cost of this quark string energy. Okay, so are these quark string important? So especially lattice QCD people use them, but they use it in many places in particle physics, from this string hadronization inside partons. So, but if there are this one-dimensional structure inside proton or nucleus, why they don't go outside? Maybe they also are important to combine nuclei. So and I think that there are these many problems with nuclear physics because they neglect this one-dimensional structure, which are absolutely crucial for the structure of proton and neutron, and should also go outside of them. So should also help with binding of nuclei. And there are these very interesting halonuclei. That there are these nuclei that have the core, but also two neutrons or protons which stay alive, which stay stable for milliseconds in very large distance, much larger than the of nuclear force. Okay, so nuclear force is below 1 femtometer has minimum, and there are like 5 femtometers. So what binds them? So there are many arguments that maybe there are indeed some one-dimensional structure. These quark strings are going outside and help this binding. What effectively acts as a three-body force, and indeed they require this three-body force. Yeah, so I believe that these one-dimensional structures are very crucial, very important, and they are nearly not included in current models. So I think there is big problem with the models. Okay, so let's go to some simpler situation with some mathematics, and finally go to these time crystals again. Okay, so to get to the simplest model of this particle is this one-dimensional Sine-Gordon model. Yeah, so we have just a lattice of pendula. And what you can see that usually the pendulum want to be down, but they can make this one rotation and still go be down. Okay? So we have this minimal configuration going from one vacuum to another vacuum. So this is stable. This hides energy. So these are like particles. Yeah. So it has some mass as this energy hidden in the structure. To release this energy, you have to meet it with antiparticle. Yeah, so we have Pei creation, we have quantization here. So we have the speed of the light, the basic propagation. But then if you build this particle, then it has to be slower because of the Lorentz contraction. Yeah, so here is the photo for resting kink, this particle, and here is traveling kink. We have exactly Lorentz contraction, the same formulas. So now you like to now there are also this as time crystal, the oscillating these kinks. So they are called breeders. So here is a resting breeder. Here is position. Here is time. So we can see that we have this pendula. We take one and it will oscillate. Yes, and this is what we see. This oscillation, this breeder. But now the traveling breeder has the time dilation. The number of ticks is smaller. Yes, so we get this kind of time crystals now. However, we can slow down these breeders. So they are not time crystals because they will stop if we don't. So okay, so they can slow down to zero. We can slow down this oscillation of this pendulum. So now we can ask how to add the time crystal. Finally, in 15 minutes. So how to add the clock to this particle. So so here is the basic model of this time Sine-Gordon-like. So we have this. So here is this kink going from here to here. And now we would like to make it to add a clock, so make it time crystal. It's a time crystal kink. So we would like that the presence of this particle gives a preference for some field oscillation. Yeah. So we have this one field phi, and now we add this second field, this quantum phase, this psi. And now this term, this minus this square, turns out it's a Lorentz invariant, so we can add it. And now in the presence of phi, of this structure of the particle, there appears tendency to activate this non-zero derivative of psi. Yeah, so this is exactly what we need for time crystals, for propulsion of the clock of electron clock, of neutrino oscillations. So this kind of mechanism, yes, the presence of particle as this phi gives tendency for the time derivative of the second field. So now if you look at this energy versus omega, the minimum is not in zero, but here or here. Yeah? So this is symmetric. So we get a time crystal. Yes, because resting now such a resting kink already would like to oscillate. Yes, energy minimization leads to periodic process. So finally, it should also create these couplet waves. So we can entirely quantum mechanics this way. Yeah, so we have very similar one-dimensional model to get this time crystal, which could lead to quantum phenomena. And here is the final model. So I will briefly talk about. So here is the Lagrangian, the final Lagrangian I'm using. So you can recognize the electromagnetic Lagrangian, F mini, F mini. However, there are more indexes because I interpret this F as curvature of deeper field, as mentioned, to make the Gauss law count the topological charge. Yeah, so I say that F is curvature on deeper field. Now the Gauss law counts the topological charge with charge quantization. Yes, and the final curvature has 4 indexes, so we need 4 indexes. So we have electromagnetic Lagrangian, but multiple of them. Also in Young-Mills, we have also these multiple electromagnetic terms. We also need this Higgs potential to prefer some shape and allow to deform to regularize singularities. So now having this electromagnetic Lagrangian. So standard electromagnetism, we have just 2 indexes. Yes. So now going from Lagrangian to Hamiltonian, we get only positive terms. Yes, we have only Hamiltonian is positive. However, having 4 indexes like here, going from Lagrangian to Hamiltonian, we have positive and negative terms. So this is very subtle that we have these negative terms like here. We have these negative curvature terms exactly as needed for the propulsion of the clock. Yeah. So this is exactly what we need. This full Lagrangian leads to Hamiltonian, which has both positive terms, which for me leads to electromagnetism, quantum mechanics, but also gravity. I can also get here, and here are the negative terms, and we can see that in these negative terms, here are the negative terms. So in the presence of this here is the quantum phase, and here is the gravitational. So literally, I get that the gravity gives tendency for the rotation of some evolution for like the quantum phase. Yeah. So the general mechanism, I have some general mechanism that the particle if including gravity has to both get the gravitational curvature. So also should finally interact gravitationally and also have the clock. And now these 2 tendencies appear together because the Hamiltonian gets the negative terms, literally coupling gravity with these time derivatives exactly as we need for the clock. Yeah, so it's very short. Okay. Okay, so we can discuss, but my time I think is finishing. Okay, so the model I'm using is very similar to Skrimian model, so they also get this very similar this Lagrangian term, and they get the nuclei. However, the difference is that they say this topological charge is not electric charge but baryon number. So for them, they don't have electromagnetism. The baryon number cannot be validated, while there are processes which require validation, like baryogenesis and Hawking radiation validates the baryon number conservation. And also we need this, they have trivial minimum of potential, so they can have only short-range interactions, and here we have Coulomb-like potential. So this is very similar to Skrimian models, but slightly different. Yeah, so different interpretation of the topological charge as electric charge instead of baryon number and Higgs potential, Higgs-like potential. And also another similar model is the lattice QCD, which have use this Lagrangian, and they believe it's fundamental. However, they use these Dirac terms, which have densities, so it's very similar to Schrödinger. So it is hides some averaging over the Feynman path, so it's not fundamental. So this Dirac term is effective. So for deeper model, you should ask what is hidden behind this Dirac term. Yeah, so we should have some deeper field which have this localized structure, like topological, and a day averaging leads to this Dirac term. Yeah, so that should be the final goal. Find this really fundamental model, not without Dirac terms, without the creation and annihilation operator. Okay. Also, I get this gravity here, but maybe let me skip it. But generally, we had this rotation of this field, so we get electromagnetism and it's quantum mechanics, because if you look at this Lagrangian, QED Lagrangian, there is electromagnetism, and there is also this quantum phase derivative times some very tiny hbar c, very tiny constant. So it's also in Lagrangian, but has much lower contribution. So indeed, we get here much lower contributions. Okay, so this similarity between dynamics, maybe let me skip it. So there are many situations with these topological vortices in nature, but let me go. But finally, if you have these topological vortices, they can there is this string hadronization. So in LHC that they assume there is string hadronization that is created this quark string and it decays into particles. So if we say that this is a topological vortex, we just need to ask what topological vortex can decay into and try to find the correspondence. Yes, and for example, it can decay into these simpler loops of this topological vortex, this loop of quark strings, and the question is which they should also correspond to some particles. The question to which one? And I think they fit perfectly to neutrinos. They are much more stable than electromagnetics, very light, three families, as you can see, and they can be created in beta decay. So very briefly, a proton neutron. So we need these fractional charges. Yes, so we have this one vortex and a knot, a second vortex around. But so what we see, you can see that this vortex around deforms vortex inside. So exactly deforms to our hedgehog, and hedgehog for us is the topological charge. Yes, so proton can just enclose this topological charge, while neutron has to compensate it. Yes, so neutron has to be minus plus minus. We get this quark structure because of this interaction with two topological vortices. So we get naturally the proper. So here are the charge distributions of proton, neutron. So neutron has to be positive core, negative shell, exactly as observed, positive core because of the interaction, and negative shell with these quarks, fractional charges. Yeah, so exactly as needed. The deuteron have electric quadrupole moment, and here indeed it has plus, minus, plus. Plus is because from these interactions, and we get electric quadrupole moment, so exactly as needed. Okay, we get the 6 quarks again, so we can explain why this matrix is so. Okay, maybe let me skip it. The neutrinos, as mentioned briefly. So finally, we would like to get the standard model. So here is standard model Lagrangian. So again, it hides both the creation and annihilation operator. So the question of what particle structure, the Dirac terms which hide Feynman path ensembles. So the question is how to get it into something smaller. Yeah. So generally, and this looking trivial Lagrangian, it is qualitatively seems a very good argument. And my time is up. So this is the summary. Yeah. So once again, time crystal should have oscillation by energy minimization. Yeah. So in theory, but they have this no-go theorem that it's not possible. However, it's crucial for quantum mechanics that indeed electron and neutrino. Yeah. So generally, relativistic quantum mechanics requires this being time crystal being oscillating already for resting particle, and if so, then they would have this coupled wave which leads to quantum phenomena like this orbit quantization. So finally, the question is how the mass of the particle, yes, literally the mass of the particle propels the clock, and we can do it. We can do it by this kind of terms of in Hamiltonian, yes, that we have the curvature squared terms which couple the time derivative with spatial derivative. Here is the structure of the particle, and it literally gives tendency for some time derivatives in presence of the particle exactly as needed. And finally, so here is the view I'm using for this for leptons, electrons. So 3 leptons, the same topological charge, but rotated by 90 degrees. So the regularization is different. So the masses are different. The neutrinos again. So we have this one-dimensional structure that need to form the loop, and there are many arguments that they should correspond to neutrinos. And so now the electron clock can look like this. Now there is just rotation, rotation restricted to the plane. You can see that it should be animation. Yeah. So okay, maybe let me switch to animation. Yeah. So for electron there is rotation. So there is quantized charge as topological as electric. This hedgehog, and the field is rotating for angular momentum and for the clock. So it cannot rotate in the other direction because it would be much more costly. So the other rotation would go to this different leptons, which are much heavier. So indeed, electron has rotation restricted to two-dimensional rotation. Yes. Why for neutrino? It would look like this. So now it's much easier to rotate in any direction. So we can see why electron has just this phase rotation, and neutrino has three-dimensional rotation between flavors, and SO3 this mixing matrix is allowed for this 180 delta CP parameter. So it's still allowed that experiments allow that it is spatial rotation. Okay, my time is up, so maybe let me finish and we can switch to discussion, and I can elaborate in discussion if somebody's interested.
I noticed George has a question earlier for page 3. He asked, in this droplet quantization, what is equivalent to Planck constant?
To which constant? Okay, so maybe let me switch to different. So there are many types of experiments. So maybe let me switch to. So they have. Okay, so I have separate slides for this this article. So here is the first quantization that they have these two droplets. So here is standing this fluid tank, and they have two droplets, and they literally make these circles around. And if they look at the diameter, it's not continuous but discrete. So we can see the quantization. Yeah. So literally the distance, they can see quantization. And also here they observe this Zeeman effect as a Coriolis force. Now they start rotating this tank, and they get this Zeeman shift literally. And another type of charge of orbit quantization they get is okay. So now they rotate. Now there is a single particle in rotating this water tank, and so now they get cyclotron analog orbit. So now the Coriolis force becomes against the Lorentz force, and now they get these standing waves. So again, so we can see the quantization. The radius is not continuous, but it's quantized. Yeah. So and literally, because these orbits are the couplet wave becomes standing wave. Yeah. So because there is this resonance condition which enforces this quantization of the quantization, which is very similar to Schrödinger equation, which also for stationary Schrödinger equation is standing wave. Yeah. So this is very similar to quantum mechanics. And here is the Zeeman effect. Yes, they start rotating this this fluid tank, getting this Zeeman splitting using Coriolis as Lorentz force. And this is the best one, the getting harmonic potential. So they use some ferrofluid and getting this harmonic this magnet for harmonic potential, and now they get this double quantization. So in 3 dimension in atomic physics we have the triple quantization. Yes, we have N, L, and M. Here there is 2 dimensions, so they have only two. Here is this R as N, is this, and here is this angular momentum. And here are the example trajectories, and they have some random switching between them. But generally, for 2 dimension, they literally get the orbit quantization. Yes, double orbit quantization. And what was the question? So I said, but so the similarity is there is similarity, but I don't remember the details. So I have read it about 10 years ago. But these articles are easy to find, and you can also find them in the slides I have linked. Okay, so maybe let me open the chat. Yes.
Yeah, George has a second question. Something about the liquid acting as a field?
Sure. So generally, yes. So my entire talk was about the similarity between liquids and quantum mechanics, electromagnetics. Yes. So sorry. So it started. So it generally starts. The basic similarity starts here. Yes. That there is this similarity between electromagnetics and hydrodynamics. So here is more complete, and it has it has the viscosity, but with zero viscosity, it becomes much simpler, so it can be simplified, something like that. So we can see that indeed they are very similar. So electromagnetics and hydrodynamics for superfluid are very similar. So, however, they miss charge quantization. So now we have just fluid. So now the question is why there is this very non-trivial configuration as charge. Yeah. So this singularity. So charge like electron is a singularity for electric field. So why it does not dissipate? Why this energy does not dissipate? So that's the magic, the mystery of particle physics. Yeah. So and yes, and we can extend hydrodynamics to include these quantized charges. Yes, these nearly singular objects which have long-range interaction by going from superfluid to liquid crystal superfluid. Yes, so now there appear these topological charges which get Coulomb-like interaction as effective as mentioned. Yes, because literally the closer that they are, the opposite charges, the lower energy, what makes them attract effectively Coulomb-like potential. So this is very similar to particle physics, and adding both the point-like defects and these vortices, we get nearly entire particle physics because of these vortices lead to intrinsic hadronization, lead to all the particles in LHC-like collisions. Yeah, so we just need this point, and yeah, so we just need these two main topological defects, and everything should we should get nearly all the particles because of the thin hadronization using LHC collisions. Okay, so I see the Ronshine. Please just unmute and ask.
Hi.
Hi.
This is a very technical, in-depth presentation. Thank you for that. I don't know the slide number. I think you just passed it while you were scrolling through here. You in the lower left quadrant there was a cubic crystal type array with nodes that were labeled as 7 lithium or 7 Li.
Oh yeah, the halo nuclei. Yeah, so sorry, this organization. Oh, sorry. I'm sorry, I have a lot of slides here. I should cut half. Yeah, I'm sorry. Okay, so halonuclei. Yeah, so there are these like lithium-11. They are known these kind of nuclei which have this one or two neutron or proton in distance many times larger than of nuclear force. Yes, it should be below one femtometer, and they are like 5 femtometers. So the question is, what binds them? It's for milliseconds, so it's very long time. So and there are three body forces. They require these three body forces. They use this Borromean description. So the question is what's
bromium,
happening?
what were the nodes in that cube? That cube
What?
lattice? Again, you had a slide in the lower left. There was like a cubic lattice structure, and each
Oh, so
node.
okay, I don't know. So if you talk about lithium, the lithium, I don't know.
You just when you were answering George's question, you scrolled past it. But I didn't get the. It didn't
So
get the.
there is link to the slides if you want. If you just maybe let me post.
Okay.
Post again the link to the slides. So,
Yeah, I was asking. I want to know what the notation. It was
three.
like
Okay.
superscript 7, and then the symbol Li. But it looked like it was a molecule. Or was that?
Oh, maybe this one. Oh, the lithium. Ah, yes, that's again lithium. Yes. So there
There
is
it
this
is. There it is.
recent. Yes. Sorry. So there is this recent article. Maybe let me put it on the chat.
Well, that's not. Yeah, that's the slide. Yeah. So it labels the node as a cluster of something and labels it as 7. Is that 7 lithium
Yes.
atoms?
So this is just
Oh, okay.
so they prepare this beryllium-7, and it makes electron capture and then produces this neutrino. Yes. So here you
Okay.
have the beryllium, and then you have lithium plus beryllium, and then they can measure the recoil from this neutrino production. Yes, so this nucleus gets some recoil, and they can measure it, and then finally they get this distribution of energy from this recoil, and then there is some width, and they can, using Heisenberg principle, then translate into uncertainty of the position. So now they can say that the size of the wave packet of the neutrino is larger than 6 picometers, which is like 1,000 times larger than nucleus. So it's huge. The neutrino is huge, but the question is what's happening there? What's the field configuration hidden in this 6 picometers? Yeah.
Is each node actually 7 lithium atoms, or is this just means lithium 7?
So there are these three types of nodes. Yes. Lithium.
Okay.
So these are just isotope.
It's an isotope. Okay.
Mhm.
All right. Thanks. And then you have so many wonderful graphics in this presentation.
Thank you.
Is this all mostly Matplotlib, or do you have some other
So there are many
tools
copy
that you
pasted, but
use to
usually there are
generate
links for the sources. Some these are made by me, for example. So some are made by me, but most are copy pasted probably.
Okay. Yeah. And I also noticed you had a lot of plots that appeared to, like these ones, that appear to simulate lines of force either for magnetism or electric fields, possibly. Is that like an open source tool of some sort that you know of that that can simulate fields, like, for example, like an electric field for a microwave antenna or something like that?
So probably there is this kind of software, but I'm not familiar. So, but generally,
Okay.
so here, if somebody would like to help. For example, here is how to add. So the electromagnetism misses the charge quantization. The charge can be a real number, and now we can work on building charge quantization as topological, but going this kind of Hamiltonian, for example, here. So, but this is very simple in simulation. So. But making it more complicated is quite difficult. So if somebody would like to help collaborate here, so on.
All right, thank
Yeah,
you.
but
Thank you for your answers.
thank you.
Ask your question, please.
Sure.
Yeah, I'm a layman, so this is a bit very advanced for me. It's quite complex, your presentation.
Too many slides, I know.
Yeah, it's extremely complex. My question is, when you talk about the time crystal, that electron and neutrons are time crystals. My first question, I wonder, so when you talk time in terms of time, whether it is can a time reversal occur or not? That's one of question. Second question, from engineering point of view, can we use electrons or neutrons to produce a kind of a clock for measurement,
Sure.
and real
Okay.
engineering clock?
Regarding the clock, so the problem is that this frequency is huge. It's like 10 to 21st hertz, I think, 22 hertz. So it's extremely high frequency. It's they measure it by using very fast electrons. That the time dilation has slowed it down. Yes, so now they were able to measure it, but generally it's extremely difficult. It's too high frequencies to use it for a clock, I think, but maybe there are ways how to make clock from 10 to 22 hertz process. Yeah, so that's very difficult. And about time symmetry, I think, yeah, so usually you can just use the minus omega. Like here I had this minus omega. Yeah, so like here. Probably omega, usually you have probably two minimum. Plus omega and minus omega. Yeah, so it should be the Lagrangian should be Lorentz invariant, and it should be time symmetry, CPT symmetry here.
Yes, thanks a lot.
And there is a related question about why you have left-handed neutrino, right-handed antineutrino. Yeah, but I have some suggestion that maybe because they have the same gravitational mass, but opposite spatial curvature. So that's very important question about neutrino. So there are some suggestions, but it's early.
Eric, could I ask a quick question?
Sure.
On your very last slide, 35, I think I understand where you're getting it somewhat, but when we talk about electrons, neutrinos, muons, the number of lobes, the hedgehog figure, where are all those lobes coming from? That intuitively, those to me describe systems with enormous numbers of particles. So why are these coming up with so many lobes in this figure? Just kind of an intuitive level.
So generally, what is the difference between the three leptons? This is the same charge, quantized charge, which here is topological. So we have the hedgehog but the hedgehog of one of the three axes, because we live in three dimensions. So we have three different axes. We have hedgehog of one axis, second or third. So this suggests why we have three leptons. So generally, there are three leptons, neutrinos, and quarks. I think because we live in three dimensions, there is this nice geometric interpretation here. I can also mention so. And why exactly the particles? So generally, I suggest here to study the string hadronization process. Yeah. So in LHC, they assume this string hadronization, that there is created this quark string, and it decays into particles. And if you say that the quark string, what is it? And the answer to this question is topological vortex. So the question is, what topological vortex can decay into? So you need to find this correspondence between what topological vortex can decay into and what they observe in LHC collisions. Yeah, so it suggests that first of all, we need these loops of topological vortex, and this is not unavoidable, should correspond to some particles. And if you think about it, it's very, very light and stable, difficult to interact with, and can oscillate in 3 dimensions. So I think it's in good argument with neutrinos. Then we can get a simple knots, and they are very nice in agreement with baryons, getting these fractional charges from interaction of two topological vortices. Yeah, so because literally one vortex around deforms vortex inside toward topological charge with electric charge for us. So baryons require charge. Sure.
Question. So if I say that part of the reason why the hedgehog figures for such simple particles as neutrinos and electrons is because those particles are actually interconnected with the entirety of the standard model. They're not really just in isolation.
So generally we have these two structure. In 3 dimensions, you have these two basic structure. One is point-like topological defect, which seems in good agreement with electric charge, quantized electric charge, and we have topological vortices, which seem in good agreement with quark strings. So there could be domains, but we really don't see domains, they are not needed. So we have just these 2 objects, and we need to ask what we can build from these objects and find the correspondence with particle physics, and doing so, this correspondence appears. Yeah, so just how to build all the particles from these 2 types of basic objects. Maybe there are some more complicated, but these are the most important.
By the way, I have to make the comment that for people who are not familiar with it, quark strings are actually the origin of superstring theory, the string theory they talk about now. But there's a huge difference of 20 orders of magnitude that was proposed as a hypothesis. But the quark strings are some of the most physically well proven structures in existence. It's just people don't talk about them because quark theory and color force are another way of saying the same thing. So I think that's intriguing how you're bringing in the proton has the same charge as a positron. That to me is just astonishing. How does this 3-particle composite
what is the difference
have exactly the same charge as a positron? And I think you're
so this is topological charge. So here topological charge, because of the Gauss law has built-in charge quantization. So yes, because our Gauss law is the Gauss-Bonnet theorem. Yes, because we say that this electric field here we use in Gauss law is curvature of some deeper field. This way, our Gauss law counts the unique number of the deeper field. So it has to be quantized. So proton and positron has the same charge. It is bent in quarks. So they have fractional, but it is at cost. So for quarks, we have these 2 quarks, but the potential has extremely high, this 1 GeV per femtometer cost of the distance between the quarks. And literally, so here we can get the fractional charge here. However, there's a conflict here, and this conflict has asymptotically linear energy density, exactly as in QCD. Yeah, so we have charge quantization as topological. It can be bent, but at a large cost. It's a cost of 1 GeV per centimeter approximately of separating the two fractional.
The topological nature of the charges is what enforces them that they must have the same.
Yes. Because our Gauss law counts some unique number of centimeter per field. So it has to be integer multiplicity of some elementary charge, but it can be bent in quarks, but it's very costly, 1 GeV per centimeter approximately.
Okay.
I see. Please unmute and ask if.
Thank you. I had a question. I'm still learning all this stuff, but one of your slides mentioned a spin 1 and spin 1/2. I was just, love this moment to hear, in your own words. Could you explain a little bit more about that? What is spin 1, spin 1/2, and also these pictures here? Could you maybe explain, enlighten a little more about what?
Yeah, I'm sorry. I went very fast. I know. I'm sorry. So here there are two-dimensional topological charges. So here, please think about going around this singularity in the center. So what's happening? Our field, if you go around here, your field will also go around and make full rotation. Yeah. So going one rotation here, your field make the same one rotation. So it means it is one topological charge 1. Yes. Here also, if you go around, your field will make one rotation, but it will be shifted by half. Yes. So but the charge is the same. So we have this Gaussian invariance. Yes. So they are the same topological charge. We interpret as spin or electric charge. Then here it is -1/2. If you go around, then your field here, then your field will go opposite direction. So we have -1 topological charge. Here you have +2 because going your field will go twice around. Yeah. So and here you have 1/2 because if you go around, your field has made from here to here. Yes, it may half rotation. However, we use field which does not distinguish this and this. Yes, we use field of ellipsoids or like in liquid crystals. We say this and this is the same. So just rotating by half rotation, you get the same. So it is 1/2 widely used in topological liquid crystals, and this is in agreement with this quantum rotation operator. Yes, that we have spin S particle. If you rotate it by theta angle, your quantum phase rotates by S times theta. Yes, this is exactly what's happening here. Yes, if you rotate this picture by some angle, then your phase, your these ellipsoids will rotate by half of this angle. Yes.
Awesome.
So
Thank you very much. Of course, I still need to, do some independent learning on this, but this is helpful. Thank you very much.
Thank you. I see another hand up. So please just unmute and ask.
So I apologize for my ignorance. I'm trying to understand this and learn this as fast as I can. And it's very fascinating because this is the foundation of what you proposed in your last talk with using that radiation of the I guess the time dilation using those lasers in a rotating fashion, one laser. So it was in the back of my mind, and I try to do some reading to understand it further. So I put this in the chat where I've noticed there's quite a lot of people that have theoretical physics and proposals out there of trying to bridge, right, between the classical and quantum mechanics of this. And I want to know from your work, what you're doing. Are you in the theoretical phase of also proposing and moving forward in this area of bridging these two things, or are you using this kind of like mathematical proofs? Because some of these things are mathematically proven. These analogies are, like in your presentation and in others, there is validation here. of
Yes,
this.
so that there are lots of questions. Yes, so the initial question yes was just
You are
why electrons are time crystals. So why they rotate? So what is required by quantum mechanics and leads to quantum mechanics? Yes, so this is the most central question here. But the final question here, the final question is here. Yeah, so we have this huge Lagrangian standard model, which looks like sorry, yeah, 11. So this is the so what's happening here? Jumps. Okay, so here is the Lagrangian standard model. It's huge, yes, and it's not fundamental because it has a creation operator. So it creates some particle. What field is the of this particle? So we don't know. So it's not fundamental. It's effective. It's an effective model. Effective model of what? So we would like to find some deeper field, which effectively is described by this huge Lagrangian. So that's the final question. Yes. So because so they work in this effective approximation perturbative, and we would like to find non-perturbative, the deepest, how as deep as possible field. Yeah, so this is my candidate, that we this electromagnetic like skirmion like term, which kinds curvature of some deeper field for charge quantization, also Higgs potential, and this way we get all everything. So this electromagnetism, but also quantum phase, this QED lower energy contribution. Also, we get gravity from boost, and we get topologically we get all the particles. So it was a very promising direction. Maybe there is requires some modification, some additional terms, but qualitatively it looks very good. But it needs help with simulation. So it's somebody who would like to help with simulation, and hopefully effectively it should be described by this effective Lagrangian of standard model. So that should be the final goal. Yeah, to get below this effective Lagrangian.
And is your goal to, on the theoretical side, to prove this with mathematical proofs, or are you looking on the applied side of things, of actually applying this, like your research group that you had, that yearly conference that you put together recently?
So there are lots of goals here, but generally,
lots of
yeah.
those.
So generally, so this is the central goal to understand physics. But what are the practical applications, if you ask? So I would say that the most practical application would be nuclear physics. So the current nuclear physics model are hand waving. There are heuristics. We don't understand nuclear physics. But this EMC effect. Yes, if you don't know, so this is the effect that if you try to take the quark models from single proton neutron to nuclei, it doesn't work. There is some deformation of quark structure. They don't understand it. So the current understanding of nuclear physics is very basic. So I think this is the most, from practical perspective, finally get very good models of nuclei. So from simulation of nuclei, and I think this is the what is missing. The current model of nuclei, I believe, are this one-dimensional structure. Yeah, there is this quark string between quark and antiquark. They consider them inside proton in neutron, but they should also go between the nuclei, nucleons inside nuclei. Yeah, so they should also help with nuclear binding. So I think this is what is missing in the current nuclear physics model. Yes, that there are one-dimensional structure and they help with binding, especially of the halo. Yes, the halo, which is much larger distance and stable binded. So probably there is some one-dimensional structure. This is quark string between. So yeah, so making it a serious simulations here, I think we could get finally nuclear physics from first principles, very good models to understand what's happening, to optimize the maybe fusion for processes, for example. So if you ask about practical applications, I think this is the most direct practical application of these kind of models. Finally, good models of nuclei.
Jarek, that's an intriguing aspect of your work. Have you had any specific progress in talking to the nuclear community about using some of your...
So it's very difficult. So the problem is that...
Very hand-wavy.
So the problem is that the mainstream people, they know what they have to do. They do it for a few generations, and they don't want to hear about some new approaches. Yeah, so it's very difficult to get into the mainstream. Yeah, so and from the other side, the non-mainstream people, everybody goes in one direction, and I try to organize people, but nobody. They just see their own model, and they are not interested in discussion. So that. There
I
are
have
social
one-
problems, I think. Yeah.
No, I have one experience with talking to someone from CERN where I argued him into the point we agreed that there was a time gradient across the lead nuclei that were colliding in the CERN collector. And the instant he agreed with it, the conversation ended because it was different from the hand wavy model that they were using. And I just found that very amusing. Maybe it's not amusing, but it's kind of ironic. But he basically agreed. And he said, oh, yeah, so there's a time phase difference across the front and the back of the two particles as they merge. The standard model that they're using did not acknowledge the existence of that time gradient and gave a different prediction. Now, it's a very subtle prediction, but the fact that all that did was in the conversation, it didn't go any further, is characteristic of some of the problems, because if you bring up a point like you're trying to do in some of these things, that maybe there's a better way to model it, but it's quite different from what you're doing, it meets with a lot of resistance. Now, this one, I didn't care much one way or the other. I just point out that you're using a computer science-ish model. And, I know computer science-ish models too. In fact, I might know them somewhat better than you do. But they're the ones that have been used. They're the ones that are standard ones that are used. And there's a lot of inertia against changing even small details.
Yeah,
Even
physicists are fixed. They have their models and they are not. So it's dangerous to use some. So it's very difficult to find who you can discuss with. So liquid crystal society. This is one direction I discuss. So I have some collaboration in liquid crystal society. However, they have simpler models. So they yeah. So it's this one direction. Another direction. I start discussing this is lattice QCD people. Yeah, so they use this kind of Lagrangian, and they believe that it's fundamental, but it's not fundamental. They have these Dirac terms which has density, which has averaging. So we need to get. They believe this is fundamental. They want to work on fundamental, but it's not fundamental. So they might be possibility to convince them to go one level down, and I believe we should get to the models I'm trying to get. Yes, to get to.
Yeah, the number of assumptions that can creep in subtly in some of these models is just astonishing, and a caution is always.
So they are very close. So this is the basic Lagrangian. So it looks very simple. So here we agree. We need this kind of electromagnetic term. But the standard one misses charge quantization, so we can add by saying that this F is curvature of deeper field, but this is effective. This is some averaging hidden. So we need to get averaging of what? We need to get deeper such that averaging of this deeper theory gets here.
I think there's a lot more people out there that are interested in this because of the synchrotron emission studies. There's a lot of people interested and doing work in this area. And I think that there's a lot more value to your work to the global community.
So if you know somebody I would like discuss, but generally everybody has own fields, and I'm not. It's very difficult to find anybody to discuss. So I think this is one direction. Talk with lattice QCD people, remind them that this is not fundamental. This Dirac is not fundamental, and we should get one step down. Search for lower theory.
Jarek, if I can make a real quick comment to Lytle, when you're talking about half spin versus full spin, they spent about a decade just screaming at each other. Well, not maybe literally screaming in some cases at each other about the very existence of half spin. So it feels like it's not an intuitive concept. Don't feel bad. It's not. Half spin should not exist in three-dimensional space.
So from one side, I have some models of particle mailing list, and many of them show this cap trick. For once, I don't disagree. This is too complicated, but this is trivial. This is literally what we need. That the quantum rotation operator that we're rotating by theta phase of spineless particle. This is exactly this. This is 1/2. This is very common. So we should use this kind of this trivial, and they use it in liquid crystals. We don't need anything more complicated here.
And that's a cool figure for that reason right there. You're giving a topological explanation for something that just twisted physicists, and it still does, actually. They just accepted, said, all right, half spin's there. We don't care how it works. No, you can't. Half spin is fundamental to how, Fermi, just the Pauli exclusion is based on that. So you can't just ignore it and pass it off and say it's fundamental, don't do it. So getting into more detail like this is just critical for saying, where do you go next on that? But again, it after a certain point, it just sets in. But again, Lotto, don't feel bad about it not being intuitive. It's not. It doesn't. If you have a fully conventional classical view, there's no easy way to see it, and yet it's there and it's important. So it's cool.
I appreciate this picture, and it helped, bridge a little gap. Now that when I go read, read about it again, educate, having this picture, I think will help me understand it a little bit more better than before, and that's the goal, right? So thank you.
Liquid crystals, there are many crystals. There are many of these kind of images. Yeah, so they get like like here. Yeah, so 1/2. Yeah, so this is exactly what I have. So in liquid crystals, they are very popular, this kind of picture. So they use it for decades. And this is exactly what we need. This is exactly satisfying the quantum rotation operator, these kind of configurations. But this is two-dimensional. So this is in plane. It happens in plane. So this is a cross section of these topological vortices. For electric charge, we need this three-dimensional version. That like here the hedgehog that making now not just going a loop around, but now we need to go one dimension up. We need to make a sphere around, let's say, and look how many times the field on this sphere wraps around this sphere. Yeah, so here he does it once, but can be also more. Yeah, so here is the. So here are this is this picture. Yeah, so generally you have this sphere to sphere, but now we only work on sphere 1 and 2-dimensional spheres. In fact, yes, in 2 dimensions you have this loop, and in 2D you have the sphere around the sphere. But this is very general.
It's also commenting.
Sure.
About this topic. Also, I'm a bit ignorant. So about the spinning. So could you say that this is to relate to the? So when you say 1 spin or half a spin or 1.5, is to do with the periodicity of the oscillation of the particle.
So this is the period is just to visualize, but can continue. So it doesn't need. So once again. So here is it's called topological charge, Windick number, also topological index, topological degree. There are many names. Yeah. So generally you take a sphere of given dimension and look at the sphere and look at the field on this sphere and having now you get the function from sphere to sphere. If you restrict your field to this sphere, and now the question is how many times this function wraps around. Yes, so it becomes discrete, and you get so this is not periodic. Just you make a sphere around your singularity and ask how many times your field wraps around itself on the sphere mathematically. Number of coverings of sphere to sphere.
Jarek, if I could put another comment on that point, there's many ways to explain about the half spin issue, but one thing that I can't help but notice is that if you have an ordinary clock with a minute, an hour hand, and a minute hand, where you have 2 cycles going on, you see a very similar type of effect, that just because the hour hand goes around once doesn't mean you're back in the same state. And if you have a clock in which you have one dial does half hours and the other one does hours, you wind up with mathematically equivalent effect of what happens with the spin rotation issue. So I like to use that occasionally as just an extremely simple way of understanding the information issue in terms of how these spins go. And there's physical analogies you can use, but an hour hand goes around once, but you're not back in the same state. The hour hand goes around 12 times, you're back in the same state. Although for a 24-hour clock, there's some things there. So
just think about this quantum rotation operator. Yeah, so that if you rotate your clock or something by some theta angle, how many what is the rotation of the field itself? Yes, if you rotate this one by let's say by pi half, then the field will rotate by 4, 1/2 of this rotation. If you rotate it by full rotation, your field will rotate by half rotation.
Yes.
Yes. If you go around, your field just made half rotation.
Yes.
So this is exactly the quantum rotation operator. This is the definition. So this is very natural interpretation for spin 1/2.
Jared, did you have any additional comments on the Casimir effect? That's something I've studied in great detail, and I find your I can't pronounce the word, the German word. You've got an interesting take on the Casimir effect.
Yeah, so they observe it, but they need shaker. The question is, what is the shaker for
Right.
physics? So, so people say some fundamental noise, 0-point energy, but no. But we have this clock. Electrons, neutrino, all the particles have some local rotations. Yes, the angular momentum. So this already creates some shaker. So I think we don't need anything more. Just the consequence of these time crystals, electrons being time crystals. Yes, so everywhere there are electrons, particles that they locally, by structure, by mass itself, create some local periodic process, some noise, which leads, for example, to Casimir effect.
One reason I find that intriguing is Casimir, and this is something I quoted in one of my slides once. Towards the end of his life, when he was asked about that, he essentially agreed with both points at the same time. There is a Casimir effect, but it is never any more than what you get by separating two metal plates. In other words, he took it back into the actual physics of the materials. So with a strategy like this, you wind up with these finite versions of the Casimir effect, which I think are, Casimir himself said that. You know, if Casimir himself said that the energy content of the Casimir effect is finite and actually quite small and was connected to the materials themselves, instead of fretting about the 0-point energy like so many people like to do, it's fun sci-fi and everything like that. Something like what you're doing here is more attached to reality, shall we say, and saying that, yeah, there's a Casimir effect, but you know what? It's got a limit, and that has impacts on modeling, because if our models assume there's an infinite 0-point energy, your model's going to be a mess. You know, it's going to have enormous numbers of calculations that don't mean anything. Yeah. And by the way, I just dissed a huge chunk of how that's done, but we have to be a little careful with the math sometimes, that we don't inadvertently make assumptions that drive the math into enormous complexity without actually providing much benefit going back. That's why I was intrigued by your slide. I think you're getting something that attaches it more back to what are the materials involved? What are the limits of Casimir mentioned? So
there is required electron clock. From many perspectives, we need electron clock. And having electron clock, we get the shaker. It also, the particles are as a shaker. We don't need anything more, I think. Yeah.
Cool.
Okay, so please unmute and just.
One question, is there an advantage of a solid versus a liquid crystal?
So what is required? If it's solid, so what is required is that there is this dynamics of rotation of these molecules. Yeah. So if you can do it, maybe you can do it. So it's solid, but yeah, probably it can be also. But something similar. I think that they make this some chiral magnets, something like that. So probably something similar can be obtained also in solid. But generally, to get this electromagnetism, this is literally the dynamics of the rotations. So you have the Higgs potential, and you just travel inside this Higgs potential. So you can say that the Goldstone bosons of the Higgs potential give electromagnetism. Yeah. So yeah, so we have just rotations like here. Yes, with just rotations, and the energy comes from the derivatives, curvature square, let's say, and it leads to the Coulomb potential effective. Cards as on qubit. Okay, do quantum physics behave the same in space vacuum? If not, so this is what's happening. Maybe this happened. So generally you have just field, yeah. So in modern physics we don't points. You can use points, but points are perturbative approximation. Yeah. So the points are I use these apples plus apple. Yeah. So you can say that apple plus apple equals to apple. So this is yes, this is true. But it's not the deepest. You can also still ask deeper question. Yes. And the deepest question in particle physics is the field. Yeah. So if we assume there is some field like electromagnetic field, and that's all. Yes, and here we just add possibility for these topological structures and interpret them as particles. So having some point, we ask what is the field configuration, and for electron, each electric field itself. So we have just field, and this field has possibility for non-trivial localized structure particles, for example, the topology. Yeah. So space vacuum. So we have just field and just the dynamics of this field. That should be the entire physics. Yes, some extension of electromagnetism. So space vacuum, I'm not certain. If not, what's happening? Maybe it can help. What's happening? And there is dynamics. Yes, so this field has dynamics. So both in spatial directions and temporal directions. Yeah. And should be effectively described by something close to this standard model Lagrangian. Yeah. So finally, we have electromagnetic-like field, so a bit extended for charge quantization, for further interactions, for topological properties, and effective description of this field should be close to this standard model Lagrangian. So you replace electron with electron creation operator, for example.
Derek, this is kind of a question, kind of a suggestion. Lyda was asking about solid crystals versus liquid crystals. When I think of those two, the difference I think of in liquid crystals is they can have states that are more complex than solid crystals. Solid crystals literally just tie everything down, lock everything to one thing. And to use that clock analogy again, you only have one hand. You can't have two separate hands in a solid crystal. You rotate the whole thing. Go ahead, Jeff.
In solid they get also these topological structures like skyrmions. Yeah. So this is I think similar, but yeah. So there are subtle differences, but you can switch I think between them.
It's a weak analogy. I'm not trying to make too much out of it.
On a physical side, could with a liquid? So it sounds like there are more geometrical nuances that are possible with liquid. But what about the frequency? Is a higher frequency possible with a solid or a crystal? Things like those practical measurements. Can I get a higher frequency with one or the other?
So here we use this as an analogy. So this is not exactly so. What I use their models, Landau-Desjardins model. It's used as the basic for liquid crystals. I combine it with the skyrmion model, getting this kind of Lagrangian. But this is only analogy. So this is not exactly. So it's kind of superfluid liquid crystal, which is more fundamental, and effective description of the superfluid liquid crystal is electromagnetism, for example. Yes. So but then the frequency you need to calculate, unfortunately. So you need to make So there are difficult calculations to get anything more. Yeah. So for frequencies you should for example prepare some answers of given shape of the particle and minimize energy, and for example try to get neutrino oscillations. So that's one direction I'd like to get, but these are very difficult calculations. Unfortunately. So it needs serious simulations, but they are very difficult.
Thank you, though. So it sounds like there are more nuances. There's not a simple answer of a frequency in a liquid. It depends on other subatomic properties.
So why frequency? So maybe velocity. So velocity is fixed. The basic velocity, yes, like here. Yes. So you have speed of light, and in liquid you have speed of sound. So you have this basic propagation speed. However, for massive particles, it is slowed down. You can slow down. Yeah. So like like in this Sine-Gordon model, like you have too many slides. I'm sorry. Like you have this very simple model. So this is nice video if you want. So here is this video of this guy this Einstein like. So that yeah. That yes, you can just I think it should be in every physics yes. For students, very simple thing, and it's very educative. You can get particle physics on that, literally. So now you have vacuum, the lowest energy state, and now here you make a particle. Yes, so you make this rotation, and now there will be this stable configuration going between one minimum and 2 pi further minimum. Yes, and so there's some hidden energy, and this particle. Oh yes, oh no, this is a particle. Yes, so it is to destroy it. It is to destroy it. You have to meet it with antiparticle. Yes, so this is exactly a particle. So it's quantized. It has some hidden energy, the mass of the particle, and now it cannot. It can no longer travel with the maximal speed, this propagation speed. Now it has to slow down. If you go toward this speed of the maximal speed, then it will you get Lorentz contraction. It will be narrower. So exactly the special relativity is there already, and you can get noise at the end. He gets this drill and get particles from. Oh yes, he gets maybe here. He gets the drill. Oh yes, the drill. Then this drill, and then from random fluctuations, you get the random particle antiparticle creation. Yeah, so it's a very nice video. I'm sending you the chat. Oh, thanks. Yes. Yeah. So if you want to understand particle physics and basics and special relativity, this is very great model to start with. Yes, the Sine-Gordon model. This is amazing. Sine-Gordon. Yes, near entire particle physics with just lattice and pendulums.
I also wanted to ask, I was recently in Ventura County.
From the thermal noise, there is creation of particle antiparticle. You can see, yeah. So this is the situation just after Big Bang, for example. Yes, you can imagine. Yes, please. Sorry, I have interrupted.
Oh no, I wanted to know if you are related to the Duda family farms here in California.
So there are lots of. No. Very popular name plant.
For me, it's Bollinger Bands and Bollinger Champagne. Don't know if I'm related either, but probably somewhere along the line.
I don't know.
Jarek, what's next?
For me,
yes,
I'm slowly developing, searching for collaborations. I don't know where, so maybe liquid crystals. I get some simple collaborations, but finally we need simulations which are difficult. So I don't know. So if somebody would be interested, help with simulations, starting with very simple. Yes, also the basic ones are like this one, recreation Coulomb potential. So this is the entire code in Mathematica. So just prepare the state and calculate energy by integrating the Hamiltonian. But finally, it's simplified, and you should get further. So there are difficult simulations to get it. So if you know somebody interested to collaboration with making some serious simulations, so I'm glad you collaborate. So that's the main next. But I also work in many different directions, like this two-way quantum computers still. Yeah. So for example, so this is one of many topics. So it's slowly developing, but need some serious collaboration for serious simulations. I'm searching all the time.
About what you're talking now, I just wonder if your work has some relevance to the nuclear fusion. There are
yes, I
so
think
much
so.
interest in nuclear fusion. So I wonder if your work is would be
So
relevant
yes,
there.
I have mentioned that yes, so that I believe the current nuclear physics model are terrible. It's hand waving some heuristics. So
Yes.
so I think having better models of nuclei should help also with optimizing parameters of nuclear fusion. Yeah. So the question is where to search for what is missing in current models of nuclei. I believe this one-dimensional structure are absolutely crucial. They are considered inside proton neutron, but they should be also considered between. Yes, I believe they are crucial for binding of nuclei. Yeah, so that literally we have protons, neutrons, and there are these one-dimensional structure quark strings which help with binding them. So finally, we should think about nuclei not like as grapes, but later as knot. This is the much better intuition for nuclei, especially for this halo that there is this single nucleons very large distance. So we require these one-dimensional structures. Yeah, so I think if you want to finally understand nuclei, there are lots of problems like this three-dimensional, like this EMC effect, that the quark structure is completely different for nuclei. If you want to go there, we should think about nuclei not as grape, but as knot.
That's brilliant. Thanks a lot. It shows there's still a lot of work there in physics.
Yeah. So I think it's very promising, but it needs help. So it makes mostly one person work. But I do it like since 2009, so 16 years. So there is slow progress.
That does seem like a nice potential there, though, because obviously the interest in fusion is so high for the energy purposes, but most of it is very much focused on brute force these days. You have the standard models, and no one's trying to refine the details of at the particle level, at least not that I'm aware of. Everything's pretty much brute force. How do we cram it in there faster? And then look at the secondary effects, which they've got wonderful models for all sorts of secondary effects. But it always turns into balancing a 1 meter strand of wet spaghetti on its end. And I've seen so many people I've known and who have represented DARPA projects, and it always winds up with that spaghetti. So anything that could contribute to this with better models could give some better precision on saying, well, what exactly you were trying to accomplish down at the particle levels between the nucleons. So as you were saying, simulations, trying out some of your models, seeing if they'd make some predictions that they could then test. Seems
We
like
need simulations, so it's too difficult to yeah. So it requires simulations.
plenty of computing, plenty of computing capacity out there these days for doing simulations. Oh my gosh!
Sure, but finding the details of the Lagrange and the potential, so there is a lot still to do here. Yeah, so it's slowly developing. So I have started 2009, but it was only qualitative, but quantitative I start 2021, so like 4 years ago. So it's quickly, relatively, it's developing. I'm finally finding some collaboration. So maybe in a few years it will be, we get to serious simulation of nuclei to finally understand, maybe try to understand fusion better and try to help you fusion, for example. Yeah. Yes, sure. This is the very important direction, but maybe also more ambitious direction. If you have nuclei, so there might be also better energy source than nuclei than fusion. I mean the stimulated proton decay. So the question is, can proton be destroyed or not? Yeah. So for example, in theory, you could make a black hole from protons, and when it evaporates with Hawking radiation, which is massless, so this way you destroy the baryons and produce energy mc square. So the question is, so if it can be done through this black hole formation, maybe it could be done without black hole. Just you have protons and try to stimulate the decay. Just try to transfer them to mc square energy. Yeah, so that would be the ultimate energy source. Yeah, so like from antimatter, but from just matter. Yeah, so mc square. So like make calculations. So this is like 0.02 grams per human lifetime. Yeah, so currently human uses this amount of energy, just 0.02 grams of energy. If you use MC square, then so if this model is right, you could think about it. So if indeed proton neutron is a simple knot, the goal would be to destroy this knot. The question is how to destroy this knot. Yeah. So for example, you could try to wiggle it to try to get this external loop outside. Yes, we need to go this internal loop out of the external loop. Yeah? So you could try to use some varying electric field and try to get it outside. Maybe having this model, we could try various ways and try to simulate. And maybe in 100 years, maybe there will be practical stimulated proton decay sources. Yeah.
Derek, do you have a reference on that NASA article about the 10 million times brighter?
Yeah, so if you have that slide, so it should be one of these two slides.
One of the pulsars on the people talk about fusion, but if you can do, as you were saying, undermine baryon conservation, which a point model doesn't give you an option for doing that, but your model at least gives you a theoretical route for exploring the possibility. That's intriguing because the amount of energy you get out of baryon violation makes fusion sound like nothing. So because you're talking about a total conversion of the mass of that.
Yeah.
But at least the fact that you give an exploration route for that's not common. I don't know of models that
so generally the standard model, they claim it's possible. So so basically we have the Gauss law which guards the number of the electric charge, but we don't have Gauss law for baryon number. So there is nothing to guard it. So it seems only local minimum, not global minimum. Yeah. So and there are many. So one hypothesized scenario is the baryogenesis, that after Big Bang there was created more baryons than antibaryons. Yeah. So it requires violation of the number. So and then the conditions were extreme. Second mainstream is the Hawking radiation. Yes, that you take baryons, build a black hole, and it evaporates into massless radiation, destroying the baryons. Yeah, so it's possible. So maybe you can do it a simpler way. And where to search it? So personally, I would search it in these centers of neutron stars. So it requires some enormous conditions, and the most extreme conditions are the center of the heaviest neutron star. So and some of them are like 10 million brighter than predicted. So I would suspect there is barium burning in the center of this neutron star. What would indeed produce a lot of energy and would prevent collapse into black hole. So I think it should be considered too.
My recollection is that some of the recent findings in astronomy, they found excesses of positrons that are way beyond what they would have expected from the usual production processes. And that would, I would think, would tend to go with the same argument you're making here, that there are processes that violate the usual baryon conservation, because where are those positrons coming from? That you have limits on how much you can generate by the usual methods. So intriguing thought that we might be looking at things that are undermining that. By the way, for folks who don't know, baryon conservation is one that just says protons stay protons, neutrons stay neutrons. It actually safeguards the vast majority of the mass in the universe and prevents it from being converted into energy. When they talk about antimatter annihilates the baryon conservation. So if you can find a way it's essentially a way of saying, how do I create the equivalent of antimatter without having antimatter is baryon conservation. So it's an incredibly powerful energy mechanism, which is equivalent to saying, hey, I've got two balls here. I can turn one into antimatter. I can turn the other, leave the other, and put them together, and boom. So people don't talk about it much, but it's a fascinating protective effect of our universe that keeps you from getting access to all that energy that's bound in there.
Yeah. So this is the
closest. Yeah, there it is. There, yeah, that's it. That was it. That's an intriguing paper. I mean, just recent. It was like 2 years ago. I got that one. Yeah. What's going on there? Anybody who thinks that we've got the universe totally figured out needs to be looking at some of the data that's coming from recent astronomy, because with new telescopes and new capabilities, the universe ain't looking quite like what we thought it was supposed to look like.
Yes, regarding new telescopes, so there are these I have proposed, I think it would be very interesting. Yes, so in the last talk, yes, so you have synchrotron radiation, you have electron on the circle, it causes excitation of the target. But from CPT perspective, this is still charge on the circle, so should also cause excitation of the target. But from our perspective, it means causing de-excitation. Yeah, so it should also literally pull photons. So we have
I remember this slide. Remember this slide, yeah.
Yeah, so both the positive radiation pressure, but also negative radiation pressure. So we are only focused now on this one, but there should be also this one. And building a camera, a telescope for this one could bring a lot of new information about the cosmos, but it's very difficult to do it. So instead of standard telescope, which has cooled detectors, we would need the telescope with pump detectors. I thought about shooting laser to the sun, but I asked astronomers what percentage of intensity of sun is the synchrotron radiation, and nobody knows. So it's a very basic question, but so if you know somebody, so we need a detector. Just take a telescope and replace the sensor with a pump sensor, and we need also monitor it. And we should be able to observe not positive, but this time negative radiation pressure from the cosmos. So it should be obtained from the synchrotron radiation, but maybe also some completely unknown currently sources. So maybe there is some sources in the cosmos which produces a lot of negative radiation pressure we currently don't observe because we don't have telescopes for negative radiation pressure. So I think doing this, it will be a breakthrough in astronomy. This kind of backward camera. So if you know somebody, I would gladly discuss, collaborate on that. Yeah, so we have just coupled to electrons. Electron here, electron here. Here we use this Feynman diagram, and here we use the opposite, CPT symmetric one. So both are possible. So we have just coupling with one electron here and one electron here, but two types of coupling, and both should be possible. But it's difficult to observe. We need a pump detector and monitor population. So yeah. But it would be amazing new information about the cosmos building this kind of telescopes. Or this hydrodynamical analog. So here is this twist-like wave behind marine propeller. It carries energy, momentum, and angular momentum. But just reversing the rotation of this propeller, now it pulls. Yes, we reverse the momentum. So we pull energy. For example, if it hits excited resonator, it should pull energy from this excited resonator. Yeah, so now we should think about photons of this negative radiation pressure. They should be also possible. Yeah, so like here, they would cause de-excitation of our target. So we need to prepare excited target, the sensor, to observe it.
I see the difficulty even on the simulation, because you would need a quantum computer to simulate this, even numerically, to figure that out for the pumping of the detector.
So from practical perspective, you just need to prepare this detector which is pumped. For example, three-state die. There are many dies that you can pump and make population inversion here. So you can prepare it. You can continuously pump it, and then if you target it to the source, maybe sun, maybe some further source, then the excitation rate should be faster. So you should monitor the population, and you should get the strength of this simulated emission coming from this target.
You make it sound so easy, but I
Yeah, but it's difficult. It's difficult. Yeah, it should be. Yes, yes, it's difficult. So probably it can be done instead of monitoring population. Probably it can be done like here. Sorry, like here. That you have here. You have this pumped. So here is this three-state atoms which will make population inversion, for example. And here is this target which acts with stimulated emission on your target. And now you put this half mirrored mirror. So it pulls photons from here, and some of them go to this mirror, and here you have standard matrix. CCD CMOS. So this is probably more practical. So if you know somebody building telescopes, so probably it could be done. Yeah. So we need to take standard telescope, replace the sensor with this one, add this half mirror, and matrix here.
For me, the question here is the funding, because this
I know
will be on the expensive side for sure.
So yeah, but if you have manufacturers of telescope and you have made the first one, then you will be able to sell them thousands of them soon for high price. Yeah. So this one direction. From the other, there are some national science and there are huge fundings for all these projects, like dark matter funding and axions and so on. So maybe how to add this kind of research to this funding. So that's the big question. So I think it's much more interesting than another dark matter non-observation. So if successful, now we are only focused on the positive. On this positive pressure, but now there is a second half of information we could get from telescopes, and we are currently ignoring it. Yes, we don't see it, but it is there. Just we need to learn to see it. And now we open another field of telescoping, astronomy.
Well, one of the difficulty with current funding strategies is for decades, the approach is you have a theory, you test it, it fails, and you postulate that you need to go 10 times more energetic, and then it will succeed. So what happens is, and part of this is human factors. People are just, you have a group, they're doing that work, so they want to keep doing that work. But it produces an extremely asymmetric funding model where you have things like supersymmetry, which has failed for decades. It's just
but you have entire society built on that. So they have a lot of people asking for money, and finally they will get it. So now you are one person. You've completed something new, so it's getting some funding. It's impossible. Yeah.
I know it really is kind of bizarre though, and supersymmetry is the one that always comes to mind, because by any normal standards you say this is the most thoroughly disproven theory in the history of humanity, but people love it so they go back to it, and you don't get funding for trying out totally new approaches.
Yeah, the main problem of physics is the human bias, I think. So so if we will not solve physics, I think AI in 10 or 20 years we just take the raw data and find the theory of everything from the raw data, and we ignore humans and just give us equations. So we have I think 10 maybe 20 years, and then computers will overcome us. Yeah.
Now, that's the good use of AI when you go to ferret out the data and find the data that you couldn't find. There are, of course, the very dangerous uses of it. And it's a razor's edge sometimes. You can go from hallucination to data ferreting very easily. And of course, right now, the bias in social uses of it is very, very much on the hallucination side, which is unfortunate because it gives a bad reputation.
So I'm referring like this. AlphaGo and AlphaGo Zero. The first one was learned on human knowledge with all this bias, and the second just started from raw data and just built from zero. So when we will reach searching for these models from raw data, ignoring human bias, I think if we quickly find the theory of everything. So I think the main thing what stops us is the human bias. All these societies which do the same because the system requires them to do so, and you cannot even if it's wrong, they will try to work with the data until they get the expected.
And our minds work that way. They have to. We have to make certain assumptions. The question is, how do we get to the point where we don't inadvertently over standardize an assumption that turns out, of course.
So generally we have to, because
what
human
Einstein
life.
did. I mean, this is not linked.
Yeah, so I understand the position of these people who are in this system and have to do as the system requires them, but I'm just saying that the totally, I think we are running in circles. There are basic questions nobody even ask. The mainstream has to do something which makes little sense, but this is the society which requires to do, yes, to be the clapping people. Yeah. Okay, so if somebody would like to collaborate here, or you know somebody, especially for simulation, maybe from this telescope building or something. So there are lots of topics. So if you find something interesting, know somebody who'd like to collaborate anywhere, I will gladly, please just contact me and we can discuss. And so there are many topics and many hopes, like here, like maybe finally some serious models of nuclear physics, maybe going toward this stimulated proton decay to give ultimate energy source, maybe toward better completely novel astronomy and other applications, also medical, I have mentioned. So there are lots of stuff, but very difficult to find people to help, unfortunately.
Jarek, I'm going to have to be going myself.
Yes,
I
also,
assume Helen's still here somewhere, but
yeah.
fantastic talk and lots of
Thank you
interesting
very much.
conversation. I like this, exploring your simple point that particles aren't really points. That is a trivially experimentally raw data fact. That's not a hypothesis, it's a fact. Because you cannot, it takes infinite energy to make a point, and every particle physicist will tell you that's why you make big physics, that's why you make big colliders, because it takes more energy. And yet
they are points in the perturbative approximation. So, and everybody knows this is only approximation. So you can write a Taylor series, but it hides something concrete. So now we can this Feynman diagram, and now we have electron, and this electron has electric field and others. So now we should ask, what is the field structure this Feynman diagram represents? And people don't do it, but you should do it.
no.
Yeah.
And interesting problems and interesting assumptions that we tend to make. I think we've had discussions in the past and why I was in the particle as a limit. I've certainly changed since then. I think that's a bit of mathematical noise that can actually wind up complicating things. We should go by the raw data, which is that nothing forms a perfect point in the physical universe. I would even go a little farther. The very concept of the point is locked into a specific inertial frame, which makes it even more limited. So you talk about a point in general relativity, you've got to be careful, because it turns out it's actually difficult to define as a pointless thing with no features in general relativity.
There are no points. The points are only in our effective perturbative approximations. If you have this electric charge, point-like charge, then integrating its energy from zero, you get infinity. If you want not to exceed mass of electron, if its electric field alone, you have to integrate from like 1.4 femtometers. This is one half of the classical electric radius. So there is required some deformation. This electric field of this perfect point has to be deformed in distance like 2-3 femtometers, and indeed, if you do it, you get the running coupling. So you can see it as just consequence of this necessary deformation, regularization of singularity to finite energy.
Okay. Again, thank you. Delightful talk and conversation, and
thank you, everybody.
So I'm going to head on off here for now. Thanks.
Thank you. So, does anybody has any question, comments? Or generally, if you have any, if you would like to have any, please contact me. We can also discuss. So, thank you.
Thank you. And I do know some people that are possibly interested in collaboration on
Sure,
working
sure.
on some 3-sat problems of attacking that. So I know some people that would be more interested in working on that, and I'll touch base with you. I'll
Yeah. I still work on that. But yes, this two-way quantum computers, and that we need to reverse the state preparation process. Yeah. So for example. Here are some. So one example is that if you use strong magnetic field before, you can enforce the spin up. If you do it before, you have preparation, and if you do it after, you get post-paration. You fix the final state, not initial. And there are many other ways. If you have both, if you can enforce final state, then you can solve NP problems. Like sure, but now you can fix the final values. Let's say of the 3-set alternatives, some verifier. Then you should find solution to your 3-set problem. So I think it's very close. So I think in months there could be 3-set solvers, but we are not prepared because the current post-quantum cryptography will not handle this. Is so I don't know what will happen then, but most of cryptography will fail. I think it's a matter of months.
Do you see people using the post-processing for error correction, or are you seeing them for the circuits themselves in the actual computation? How do you see this on the post-processing side of things?
So this is just how to solve NP problems having this additional post-paration operation, which would be possible to do CPT symmetry of physics, and there are many ways to how to realize it. In theory, now we have to show it in practice. So there are also some error correction new capabilities. So for example, you get this kind of equalizer that it requires these 2 qubits to be equal, for example. So usually you just measure it, this qubit, and here you can enforce it to 0. This way you work on copies of qubits. So you can get classical error correction practically. So I think it should also improve with error correction, having this post-paration operation.
That may be the moneymaker right there. You never know.
Yes, but you need the technology. So it is upgrade of current technologies, and in Poland you have, I think, 1, maybe 2 quantum computers on 5 qubits. So not in Poland. So the producers of these hundreds qubit quantum computers will quickly be. So yeah, so I think cryptography current will be cracked in months to years maybe. And the post quantum is not the current post quantum is too weak. I think we need to make a post quantum which is resistant at least to potential quantum NP solvers. The current one is not.
Okay, sir. Thank you. I will
Thank
reach
you.
out to you in the near future.
Yes, thanks.
Thank you for a great presentation.
Thank you for great discussion and questions. Okay, does anybody has any more questions, comments? If not, so thank you very much for the attention, and please contact me if something. The organizer are still there, or probably organizer have left, or. Okay, so I think I will finish now. So thank you, and please contact me if something.
So thank you for all coming.
So sorry for the prolonging. So have a nice evening, and
You too.
see
Thank
you
you.
next time. Thanks. Thank you.